So welcome to math class. Okay, so what I have right here in the first part is just a list of things off your formula sheet. So this is copied and pasted from your formula sheet, and we have talked about the first two. So when you look, this is the Maclaurin series. I haven't actually done a Taylor series for you. So we've just talked about if we want to center it around something other than 0, then we're going to be substituting in that value. So if you were substituting in, if you were centering it around 2, you would substitute in 2 for all your A's. And so you would have that change, as well as the fact that the actual polynomial itself is shifted over. So you would have like x minus 2 squared and stuff like that. So actually, I was going to see, we are going to do one Taylor series today if we get far enough. Okay, now the next two things on your formula sheet, it says it's adding a Taylor series. So if you look, these two look the same. They're kind of giving you the pattern here that by the time you get out to the nth one, it would be x minus a to the n over n factorial, and the nth derivative evaluated at a, plus an error term. So what they're saying is you can bound the rest of it. It's kind of like what we did with the integral test, where we could bound the error. This term right here, this r sub n of x, this is the Lagrange form of that. This is what we're going to use to have an upper bound on our error. And so we're going to use that formula. Let's say that we do a polynomial and we only do, say, up to the x to the third, or something like that. We can figure out an upper bound on our error. Now, it can be substantially larger than your actual error, okay? But it definitely will not be higher than what you get from this particular form, okay? And we'll talk about and define all of those variables for you. It's nice that it tells you here that C lies between A and X, okay? And you're actually going to choose C so that it maximizes the error. That's how you're going to choose it when it says it lies between A and X. But I'll define all those variables when we get there. Okay. So this first one says, find an upper bound on the error when using the Maclaurin polynomial of the given degree to approximate the following function for x equals 0.5, include an approximation of f of 0.5. Okay. And so the function that they're giving me is e to the x squared. So I'm just going to write that up here for a second. And our calculator can find that for us. Okay, so we're just going to see what it actually is to kind of give us a feel for how we're doing. So that would just be doing e to the 0.5 squared. And I'm actually just going to let y'all put that in on the calculator. Tell me what you get. You got what? Oh. That's a commitment right there. I would have gone and got a calculator for that. My goodness. Feeling the bro love today. It seems like you're trying to add some in. I don't know.
Well, someone's got to go to shame.
Someone's got to spill the cheese.
I had my German.
It's like 1.28400054166.
1.284, do it for scratch, for starters. All right. So now what I'm going to do is get a Maclaurin polynomial. So I'm going to start with f of x is e to the x squared. And I need to evaluate the function at 0. So that would just come out to be e to the 0 squared. Or e to the 0, which is beautiful. Okay, and then I'm going to get a series of derivatives and evaluate it at 0, because that's what I need to substitute into the Maclaurin series formula. So f prime of x, help me out. Yes. My mind doesn't work in that order, but she's absolutely right. So the derivative of the x is e to the x. The derivative of e to the x squared is e to the x squared times the derivative of the exponent, which is 2x. Okay, so I need to substitute 0 into that. So what is that going to be? 0. Okay, because you'll have 2 times 0 times 1, so that's just 0. So we're going to take another derivative. And what rule am I going to have to use? Product rule, and I have to do it backwards because Vernetti went and put the 2x in the front. So here we go. So we're going to have the first derivative of the second. Wait. Yuck. So that's first times derivative of the second plus the second derivative of the first. So I'm kind of in the mood for simplifying that a little bit. That would be 4x squared e to the x squared plus 2e to the x squared. For some reason my plus looks like an exponent. Okay, so we want to substitute 0 into that. Alright, so that part's just 0 and then plus 2. Okay, now it's actually, that's as far as I'm going to need because it said P2 of x, okay? But that's as much as I need to write my Maclaurin because it just wanted the second degree. However, in this formula, they're going to want you to use the third derivative. So you're going to need one higher derivative than whatever you needed from Maclaurin. So I'm going to go ahead and figure out what that is while I'm like on a roll of derivatives. But that was as far as I need to plug in my Maclaurin formula in just a second. But let's go ahead and get the third while we're at it. So you'll always do one more. So I've got to do product rule on the first part. And I'm going to group it like that. So you could leave the 4 out as a constant, but I'm just going to put it as part of the first term. So I'm going to have the first. All right, go ahead. Tell me the derivative of the second. Gross. I do when it's a constant, but not when it's a variable. I don't know why. But I asked you for the answer, so I got to go with it. Okay, plus the second. How about times the derivative first? 8x. Okay. So I guess I'll simplify that. So it would be 8x cubed e to the x squared plus 8x e to the x squared. Well, look, I moved it in front like you after all. What? Oh, that would be helpful. What about, thank you. What about the derivative of this guy? Alright. Oh dear, thank you. F triple prime. You're catching me all kinds of places. Well, I think I can combine these two. What do you think? I agree. Very astute. Okay, now I don't need to evaluate that at 0. This is just for my error term. And I'll figure that part out in a minute. That's supposed to say for, not form. It's going to be for my error term. So let's write our actual second degree polynomial. And I'm just going to write the formula. The formula makes me happy, okay, that they give it to me. So I'm going to write it as f of 0 plus f prime of 0x. Now here I'm going to move it to the front. I like this part in the front. I like to write this part as the coefficient of x squared. Okay, so that's how I'm going to write it. But I'm just copying it from my formula sheet. And that's as far as I'm going to need because they only asked me for the second degree polynomial. And so we're just going to substitute in. So my f of 0 was 1. My f prime of 0 was 0, so I don't even need that. F double prime of 0 was 2, so I'll just go ahead and write this. Plus 0x plus 2 over 2 factorial x squared. So it's just 1 plus x squared. So that's our approximation for e to the x squared that we're using. We're saying it's about 1 plus x squared. We didn't go to a whole lot of effort there. But I could figure out my approximation for f of 0.5. Okay, so it would be about 1 plus 0.5 squared, which is 1.25. So not too bad. I mean, it's 1.284. And we got 1.125, and we didn't do very many terms. Okay, so that's not bad. So what we're going to do is find the max error. The actual error is pretty small. Okay, but this full number you should expect to be larger. I'm already out of room, so I'm just going to do the error on another sheet. All right, so the formula for max error, I am copying. I would never be able to do this without a formula sheet because I would never remember it. It just doesn't come up often enough. And it tells me C, well, it's between A and X.
Oh, so max error is the range.
Yes. Okay, it tells me that C is between A and X, so I'm going to write that part down. Okay, and I'm going to define all the variables for you. Okay, N is the degree of the polynomial used to approximate the function. Okay, so what is N for me? 2. My N is 2 because they asked for a second degree polynomial. My polynomial was 1 plus x squared. A is the value the function is centered about. Mine was a Maclaurin series, so what was mine centered about?
0.
You got it. Okay. X is the value that you're evaluating the function at. You got it. Okay, and then C is just going to lie between A and X. So for me, that's going to be between 0 and 0.5. Now it's always going to be one of the endpoints. It's either going to be 0 or 0.5. You're going to choose whichever one would maximize the error. Okay, so I'm going to say whatever maximizes the error, and it will be an endpoint. So now we're going to try to substitute all that stuff into that formula. And that'll give us our max error. Okay. So this will be the error in the second degree polynomial. So n was 2. So the R2 of x, the error that I got in the second degree polynomial. This is n plus 1. And this is representing the derivative. So they do it like that because it's like you're not going to be putting a bunch of prime things, even if it was only the second derivative. So this is going to be the third derivative evaluated at C. And C is going to be whatever makes it the biggest, between 0 and 0.5. So you're going to put that value into the third derivative over what factorial? 3 factorial, because n is 2. And then we're going to have x minus a, my x, where I'm evaluating this function as 0.5, minus what it's centered about, and raised to the what? Third power. So that's what I have to figure out. It's just going to be a number answer. So if I look at my third derivative, was this guy. So you have to decide, would your third derivative be larger at 0 or at 0.5? Yep, because what's it going to be at 0? 0. Okay, so this is going to be the triple prime at 0.5. So we'll just say C is 0.5. Okay, And so I'm just going to put that in. So it'll be 8 times 0.5 cubed times e to the 0.5 squared plus 12 times 0.5 times e to the 0.5 squared. Okay, and that's just the third derivative that we already calculated. We're plugging in 0.5 over 3 factorial times 0.5 to the third. Now, I want you to try to put that in on your calculator and see what you get. I'll put in approximate. Just gonna pause it. Alright, so after much work, this is the answer that we got. And the only problem we had with calculating, or the only one that was in particular, is you can't just put the 0.5 cubed in the numerator unless you put all of this in parentheses. So otherwise it'll just multiply the 0.5 cubed times the last part. Okay, and so that was the error we had. Now, did we really have that much error in what we did? Yeah, because we were really only off by like 0.03 between these. So this is really like 6 times our error or more. Okay, so it's truly an upper bound for the error, and that's actually a question they ask on one of the IB questions. And they have you calculate it, and they say how good an estimate is it, and what they wanted was it was much larger than the actual error. And I suspect while I'm referring to a specific problem, I would suspect that's typically the same. Okay, so just kind of be on the lookout for that. All right, so we killed that one. Now this one says, show that the Maclaurin series for this is equal to that, and find the radius of convergence and the interval of convergence. I don't know. You want to do this one first or a Taylor series first? You got a preference? Okay. All right. This is the big one, and the other one's not so bad.
Let's get the big one out of the way.
Okay. All right. So for this one, if we're doing a Maclaurin series, so you haven't done Taylor yet, I've got one Taylor series one for you for today. We're going to do a series of derivatives. So while I have this, and that's the easiest form for substituting in 0. So Maclaurin implies that it's centered around 0. And that was our A value, right? And just to warn you, your book uses C instead of A and confuses the whole issue. Because then you have a C in the other formula. It can make you crazy in the error formula. Okay, so if I do f of 0, that's going to be 1 over the square root of 4. So that's 1/2. That kind of makes me feel good because there's like a half in this. But I'm going to rewrite it in order to take the derivative as 4 minus x to the negative 1/2, because that'll just make it easy to use the power rule. So f prime of x, so as far as how far I have to go far enough to kind of find the pattern. I would say we're probably going to end up going to the third because they showed me to the third, and I feel like I would need to know that far to recognize that pattern they're trying to get at. Also, they didn't expect me to be able to recognize that pattern. That's what they told me. That's why they told me what it was. Okay, because you have to recognize the pattern to be able to do the series tests that we know. So anyhow, derivative. Okay, so if I rewrote it, it'd be like positive 1/2, and I'm going to move this to the denominator. That's supposed to say 3/2. I don't know if that 3 is clear enough. All right. So if I put in 0, I'd have 1 over 2 times 4 minus 0, so 4 to the 3/2. And if you'll remember, for rational exponents, the bottom number, you take the root, the top number, you raise it to that power, so you're taking the square root of 4, which is cubing it, which is 8. Now I'm going to leave that as 1 over 2 times 8 instead of saying 16. And the reason is, I'm looking up here, they're going to be wanting me to take some 8s out of the denominator. So I'm going to try to break whatever answer I get down into some 8s. I would not do that if I wasn't going for what they told me. That would not occur to me. Okay, so we're going to take another derivative. And it's easier in this form, so I'll just go ahead and make that plus plus, so we can kind of ignore the 1 and just do this. So we're doing the negative 3/2 times the 1/2. And then 4 minus x to the perfect times negative 1. Okay, so we're going to go ahead again and just make that positive. And I'm going to write it as a fraction because to me that's easier for substituting in. So we'll need f double prime of 0, and we'll have 3 over 4 times, when you put in 0, 4 to the 5/2. So we're taking the square root of 4, which is 2, and then we're going to have 2 to the 5th. Okay, so what I've got is 4 times 2 to the 5th, and I want to get as many 8s out of that as possible. So it's like 2 squared and 2 to the 5th. So that's 2 to the 7th. How many 8s can I get out of that? 2, because it's like 2 cubed times 2 cubed times 2. Okay, so this guy would be 2 times 8 squared, and that's 3. Now you can do that whatever you want. You know, if you'd rather get the final number, just put it on your calculator, 4 times 4 to the 5/2, and then like divide by 8 a couple of times, see how many 8s you can get out of it and what's left. That's also okay. That's just kind of how I thought about it. Alright, so here we go. F triple prime, last one we need actually, would be what? And then 4 minus x to the negative. And then we're on to them. We're just going to make that positive. So we'll have 15 over 8, 4 minus x to the 7/2. I guess I'll just do my f triple prime underneath it. Now I don't have to do an extra derivative unless they ask me for the error, and they didn't ask me for error on this one. So I would do 1 extra if they wanted the error in the third term. But I think the radius and interval of convergence will satisfy our desire for this problem. So we'll have 15 over 8, 4 to the 7/2. So 15 over 8, and that would be 2 to the 7th. And we already kind of said 2 to the 7th was 2 to the 3rd, 2 to the 3rd, and 2. So it seems to me we have a 2, and we have 3 8s. Is that okay? Can I go back to the other spot? Sydney? Can I go back over here now? Oh, Rachel, can I go back over there? You know me, I can't tell who's telling me what. Alright, so here we go. F of x. And I'm just going to write the formula. You don't have to write the formula every time if you don't want to. For some reason, I get great satisfaction from just knowing all I'm doing is substituting into this formula. It just makes me feel like I'm going to get it right. I'm not going to forget to divide by a factorial or anything like that. So I'm just going to substitute in. F of 0 was a half. I'm going to leave it just like I had it. 1 over 2 times 8x. And then this one was 3 over, and I'm just going to put my 2 2's. the 2 factorial and this. And then this one was 15, and I'm going to have 3 factorial is what? 6, and the 8 cubed. Okay, so hopefully you can see that I'm just putting the derivative that I had, and this is my 3 factorial. Oh, yes, that would be helpful. Thank you. Okay. So that's what I got, and they're trying to get me to show that it's this, so I'm going to take out a half. If I take out a half, it should look good. Oh, I should have left it 3 factorial instead of calling it 6. That's kind of a bummer. But that's okay. Minor adjustment. We can persevere. So if you take out a half, that leaves you 1 plus 1/8 x. And then we have 3. That 2's gone. We'd have 2 times 8 squared. I'm going to do that as parentheses. And then we have the 15, but they wrote it as 1 times 3 times 5, so I'm pretty sure that that's the same thing, and the 3 is 1 times 3, so I'm okay with that. Took out a 2, and I had the 6, which they wrote as 3 factorial, and the 8 cubed. Okay, now they said to show that that was the same as this, and I feel like I have. Okay, I mean, we see the pattern in the top. It's every other, you know, and I think I'm just good with that. Okay, so I think I have shown that. Alright, so what I know now is, and if you wanted to be like super cool, you could write their last term right here. I do not have room to write that last term right there, but we would just kind of be, if I was trying to get marks, I might do it just to make sure. A dot, dot, dot in that last term, just to say, hey, yeah, we got the pattern. Okay, so now what we have is a summation from n equals, do we think it's going to be 0? Yeah, I think so. And so our pattern is that we have the 1/2, we can't forget the 1/2, and we have 1 times 3 times 5 times dot, 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 2n minus 1. Over n factorial 8 to the n x to the n. So that's our infinite series, and we want to see if find its interval of convergence and radius of convergence. So what beautiful test are we going to start with? I think so. All right. So I'm going to have the limit as n approaches infinity, absolute value, and I'm going to have this with n plus 1's everywhere. Now I'm just going to write the half right here, just because I feel like it. You do what you want, but I'm establishing a pattern so that I know what I can cancel. So. It's not that 15 is not equivalent to that. I'm not debating the mathematical truth. So this would be 2 times n plus 1 minus 1. And I would have, I'm going to put this in the numerator, the x to the n also, so that'd be x to the n plus 1. And then I have n plus 1 factorial, 8 to the n plus 1. Okay, so all of that is just the n plus 1 part. And then you divide by the original, or times the reciprocal. So I'm going to have the half, 1 times 3 times 5 times dot, 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 2n minus 1, and the x to the n, and the n factorial, and the 8 to the n. So this little guy right here, I'm just going to like figure out what this is. So this is 2n plus 2 minus 1. Yeah, so that last one is just going to be 2n plus 1. Okay. And so the pattern of this, though, is every other. Okay, so we're going to have to think about what's going to be before that. But first, I don't know. Anything you want to get rid of before I write the next line? Okay. All right, so I'm going to cross out the halves, and then I think I'll go ahead and write these out separately. I mean, do you want to cross these out and just put an 8?
Yes.
I mean, y'all are good with that. You've established that. Okay. I think you're pretty good with these.
Cross the factorial and the factorial.
Okay. So then we just need to figure out how to deal with that other factorial that goes like every other one. So that's good. That'll save us a little. Okay, so this, if you think of, what about the x's? You want to do that too? So that would leave what in the numerator? Okay, good call. No, it's x to the 1. And that's just going to be x up there. Whew, we crossed out a lot of stuff. I got to see what we got left here. All right, so we've got this 1 times 3 times 5. I'm going to leave a little room. It goes all the way up to 2n plus 1, but I need to figure out like what comes right before that. So I still have that. I still have an x in the numerator. That's it for the numerator. I have an n plus 1 and an 8. And then I've got this guy, the 1 times 3 times 5, dot, 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 2n minus 1. So it's usually the larger one that you break, factorial that you break down, and this is larger because 2n plus 1 is larger than 2n minus 1. But the pattern is every other factorial. So the term right before it has to be 2 before it instead of 1 before it. It's 2n minus 1. Okay, because you see there's a difference of 2 between each one. Okay, so instead of going down 1, I'm going down 2. And that's kind of nice. Why? This is starting to look better. Here's some weights. Alright, so when I look at all that, I'm going to take the x out. I want to figure out where this is less than 1. So the x is going to come out, and that just leaves me the limit as n approaches infinity. I'd have 2n plus 1 in the numerator and 8n plus 8 in the denominator. Starting to look promising. And so what's the limit as n approaches infinity of that? And then what should I do? Alright, so we know that this at least works between negative 4 and 4. We need to determine if it works at the endpoints. Okay? And so, I am going to try, which one first do you think? 4. The larger one first, because sometimes it saves me work, and in fact, this is going to be the perfect example of saving me work. I'm so excited. So I'm actually just putting a 4 into this right there. Okay, so I'm going to copy that, only there's going to be a 4 in for the x. But since you can't see that, I kind of wanted to show it to you. So 1/2. Sorry, that cough probably sounded dreadfully loud. I've been told you can randomly scare people. Loud sounds in the microphone. You know, a well-placed evil cowbell could be.
Mrs. Stark scared
She's
the
scared of
bridges
the
off of
cheeses
Jason
off.
yesterday.
She was like, so she came over to, and it's okay if I talk about this, this is what fucking Boston, right?
Yeah, I'm a full ID, and they'll be like, oh,
Okay, we have to figure out what's going on with this. Do you see anything that remotely looks like anything?
Nope. This sucks.
There's another thing we can do, because we can't do limit test, because the limit test because I don't want a formula. Because the point of doing the limit test in the first place is to find where it's equal to 1. So if you do the limit test again right now, it'll just get equal to 1.
But I think it's going to go to 0 if you do the limit test because, I mean, this is bigger in the bottom if you compare this and this. And n factorial would be bigger than that because this is doing every single number and this one's doing every other.
But it's also times 1/2.
And which is to make it,
We have to hope.
no, I mean, I'm just saying it's not nth term. You were saying limit? Are you saying limit? Well, let me suggest one little thing to you. See if this affects your thought process at all.
Because then you'd have 2 1/2s also. It's 4/8.
That's true. But what's 1/2 to the n by itself? Geometric. So how about I compare to a geometric? So take your limit compare idea, but do it with a geometric. What do you think? Okay, well that's what we're doing, so just, okay.
I'll know about that.
Well, I mean, good luck.
Make it work.
Limit comparison, I already gave up. Now, I made it fit on my original, but when I try to be clear, I tend to write larger.
Every time I've had to write the 1 times 3 times 5 and then ... it's just aggravating.
I don't blame you. Okay, it converges because r is 1/2. So I'm going to do the limit as n approaches infinity of mine divided by what I'm comparing to. So here's mine. I'm also aggravated with all the ... dots. Okay, I just made that 4/8 to the n in the numerator, 1/2 to the n. So that's just my sequence, and I'm going to divide by the sequence I'm comparing to, which is 1/2 to the n. And I still got to figure out what the rest of that goes to. Do you have a thought about what you think the rest of that goes to? Yes. Why 0?
Because the factor on the bottom is bigger than the factor on the top.
Yep. And plus they threw in a 2, just to okay, so this is every single number in the factorial. This is every other number in the factorial. So if I have all of them, this is going to be bigger in the bottom. And they also stuck a random 2 in the bottom. Okay, so this is going to 0, which, is that positive and finite? All right, that's what I wanted to hear. So if it's not positive and finite, we still have hope. Okay, so if you'll remember, if you get 0, if what you're comparing to converges, yours converges as well. And mine was, so I'm okay. So therefore, and I'm not going to say it's positive and finite, because it's certainly not positive. I'm just going to say, therefore, converges. They don't make me say, like, all that. I've already kind of said it, that what I was comparing to converges. So converges by limit comparison. Okay, so that was the, what did I put in? 4, so we know that's an or equal to. Now, thank God, it's going to get shorter because it's going to be the same thing. Now I'm testing the -4, which is just all that same stuff with a -4. So, kind of convergence do I have? I have absolute convergence. Okay, so this is the same thing, only alternating because it's negative 4/8 to the n. Or you could make it like, you could take the negative 1 out if you want. So it's like negative 1 to the n, and then like the same thing I had before. You don't actually have to show that. You just have to recognize it. So this is the same thing I had before, only alternating, and you know if it converges when all the terms are positive, then it converges if every other term is negative. So this has absolute convergence. I'm just going to say that. And so we include both endpoints, and that is our interval of convergence. I like it. I don't know why everybody doesn't do that. Like, that's what I want to include. Shouldn't I underline it? I mean, you know, no one else in the world will know what we're doing, but, you know, works for me. Okay, so that was like the big one. We only have one more left. Are you okay with that one?
Yeah, maybe we should get a class bathroom break.
This one is your first Taylor series that you've ever done. Special moment for you all. It's just the same thing, okay? You're going to be doing a series of derivatives, but you're going to be evaluating it at 1, what they told you to center it around, instead of evaluating it at 0, okay? And then also in the formula, instead of it being x's, like x squared and so on, it'll be x minus 1 quantity squared, x minus 1 quantity cubed. But I'm just going to go straight to my formula sheet and not worry about that. So you're just going to do f of x, and then whatever they want to center it around, you find that. So f of 1 is 0. And then you're going to find the first derivative, which is, and so f prime of 1 is, and I'm going to make that x to the negative 1 so that I can do power rule. And the next derivative, and just so I can substitute in, I'm going to move that to the denominator because I don't think in negative exponents. So if I put in 1, it said 4th degree, so I'm going to have to do 4 of these. However, if you kind of look ahead, it says using the 4th degree Taylor polynomial as approximation, find the max error. So I need 4 for the first part, but I'm going to need 5 to get the error term. Okay, so that's how far we're going to go. Then they always tell you how far to go, because otherwise you could be there forever, literally. All right, so the derivative. Okay, and so that would be 2 over x cubed. So f, oh, wait a minute, I need a prime on that guy. It would be 2. And the 4th derivative. So the 4th derivative at 1. Okay, so that's kind of as far as I need for the polynomial, but I'm going to take one more derivative because I see that they're going to want the error term in a minute. So what is that? And I'll just go ahead and write that. Okay, so that's just for later for the error term. Okay, and this is the formula for the Taylor series. It's the same thing, only we're putting in A, which for us is going to be 1 all the way through. But I'm just writing the formula for now, and then all your x's are like x minus a's. So this would be f double prime of a over 2 factorial x minus a squared, dot, dot, dot. Okay, so that's from the formula sheet, with the exception that I like to write that as a coefficient. So for me, ln of x, which is my f of x, is all my a's are 1. So f of 1, so 0. f prime of a would be what? Times x minus, okay, and then f double prime would be negative 1 over 2, because 2 factorial is 2, x minus 1 squared. And then for the triple prime, bless you, I would need 2 over 3 factorial, x minus 1 cubed. And then for the fourth one, I would need negative 6 over 4 factorial, x minus 1 to the fourth. And so I'm just going to rewrite that. So it would be x minus 1 minus a half, x minus 1 squared. That would be 2 over 6, so a third. X minus 1 cubed. And then, what about this one? And that's like 24, yeah, so minus 1/4. X minus 1 to the fourth. And so that's our approximation for ln of x. And any questions on that? Okay, so all I have left to do is find the error in that. Okay, and it's a little bit weird. It says using the fourth degree polynomial, that's the one I just found, as approximation for the function, find the max error. And this is a little weird because they're saying that you're plugging in anything between a half and 3/2. So instead of telling you actually what you're plugging in, they're saying what's the most error that you could have if you plugged in anything in between that. And again, it's going to end up being an endpoint. You don't have to worry like in between values. So I'm going to write that awful formula. It's not as awful because they're nice enough to tell me what everything, they're nice enough to give it to me. I don't have to memorize it. They don't exactly tell me everything that stands for, but they do tell me on the formula sheet C lies between A and X. Okay, so let's think about all my variables. What is my N? Okay, that is A. I agree with you. N is 4. It's whatever polynomial, whatever the degree of the polynomial you approximated with was, and ours was a 4th degree, and they also tell me right here. And then Sam's right, it's centered around 1. That's your A. What else do I need to know? Yeah, C and X. Okay, so we're going to have to, X is somewhere between there. And then C, if we think about A, is 1. So between A and X, well, that could either be between 1 and 3/2 or between a half and 1. So what that ends up all together is basically C is going to be between a half and 3/2. Because if you're between a half and 1 or between 1 and 3/2, then somehow you're between a half and 3/2. Okay, so let's see what we can do with this. So this would be, if it's the n plus first derivative, that's really just the 5th derivative at C over what factorial? 5 factorial. I'm a little confused about this x business, so I'm just going to put x. I know the A, and I've got the 5. Now, I also know the 5th derivative. Okay, so we found that already. It's 24 over x to the 5th, and I'm supposed to plug c into it. So I'm going to write it as 24 over c to the 5th. I'll deal with c when I figure out what it is. Okay, so this would be 24 over c to the 5th, 5 factorial, and I still got, like, not really sure what this is. Now, x has got to be between a half and 3/2. You're always making it as big as possible. But if you have 3/2 minus 1, you're going to get a half. And if you do a half minus 1, you're going to get negative 1/2. Okay, so really when you deal with this, you're really talking about the absolute value of the error. What's the most you could have? So it really doesn't matter. The magnitude of both of those is the same as far as whether positive or negative. It's still an amount of error. So sometimes you'll just see what's the magnitude of the error. So honestly, it doesn't matter. I'm just going to put in 3/2 because I'm trying to see not am I over or under, but what's the most error I can have. If you put a half, you're just going to get the same thing, only negative. But it's the magnitude of the error. Okay, and so then the only thing else I have to decide, so the x didn't really matter that much, okay, in this situation, because it's centered, I mean, it was right around, and it's always going to be that way, the interval that it's centered. Okay, and then the last thing I have to decide, so almost perfect timing for my people going to the college thing, is what C should be. Between a half and 3/2, what would make this as large as possible? 1/2, okay, because you want to divide by as small a number as possible. So if you just put in 1/2 into this, that's going to give you your error, and I'm just going to tell you what it is because I got people leaving, and that's that. And that's actually the end of the notes part. Okay, and those of you still here, this is not going to be 1BII, it's going to be 1CII. And so you got some hints and stuff like that. Might just be good if our designated person took a picture of this and the pages in the option book and put it in.
This is